Hello everyone, this is Bini R from the Department of Computer Science and Engineering at Emmanuel Ursa JJ College of Engineering. Today, I am going to explain binary trees, an important concept in data structures. In real life, we use similar structures to organize information like family trees, company hierarchy, and file systems. Let's begin with the basics. Now we can discuss about introduction to trees. What is a tree? A tree is a hierarchical structure made of nodes. Let's think of a family tree. The oldest person is like the root. Children and grandchildren form the branches. Each person, that is node, is connected through one path only. There are no loops, just like in a real family. You cannot come back to the same person through another path. Also, if there are n people, there will be n minus 1 relationships, that is, edges connecting them. So, we learn a tree is a collection of nodes where one node is designated as the root. Every other node is connected by exactly one path from the root. There are no cycles or loops. A tree with n nodes always has n minus 1 edges. Now we can see some basic terminology. So first we can see about the root. The root is the topmost node of the tree. Let's relate terms to a company structure. Root, CEO of the company. Node, a basic element containing data. Node means any employee in the company. Next we can see about the edge, a link connecting two nodes. So the relationship between an employee and the CEO is one of the example. Parent, a node that has children is called parent. So here manager is the parent. Child node, a node derived from another node is called child. So here employee under the manager is called a child. Then a leaf node. A node with no children is called a leaf node. So employee with no subordinates are called leaf. Now we can see about internal node. Internal node is the manager, a node with at least one child. Sibling, nodes sharing the same parent. So employees under the same manager comes under sibling. Next, level. Position of a node in the tree are known as level. So position in hierarchy, that is CEO is level 0, manager level 1, etc. Next, the height, number of edges in the longest path from root to a leaf. So maximum number of levels in the company comes under height. Next, the depth, distance from the root to a node is called depth. So distance from CEO to a specific employee is called depth. Subtree, a tree formed by a node and its descendants. So subtree means a department with a company. A department within the company is known as subtree. Now we can discuss an example of a tree. Let's understand this diagram using a college system. Let's consider A as principal, that is root, B, C, D as heads of departments, E, F, G as faculty members. So faculty members E, F, G are leaf nodes because they don't manage others. This structure helps organize responsibilities clearly. Now we can discuss about root. The root node is the topmost node in a tree. It is the starting point of the structure. In this example, A is the root node because all other nodes come from it. Let's consider an example. Think of a company. The CEO is at the top. The CEO is like the root node. Now we can discuss about parent and child node. A parent node is a node that has one or more children. A child node is a node that comes from another node. Let's see the diagram. A is the parent of B, C and D. B is also a parent because it has children E and F. D is the parent of G. Let's think a real life example. This is just like a family. Parents have children, children come from parents. Now we can discuss about sibling nodes. Sibling nodes are nodes that share the same parent. Let's see the diagram. B, C and D are siblings because they all have the same parent A. E and F are siblings because they share parent B. Consider a real life example, just like brothers and sisters in a family. Now we can discuss about leaf node. Leaf nodes are defined as nodes that do not have any children. They represent the terminal or ending points of a tree. Since no branches extend from them, they appear at the lowest level of the hierarchy. Let's consider the diagram. At the top, A is the root node. Nodes B, C and D are its children. Node B further branches into E and F and node D branches into G. However, nodes E, F, C and G do not have any children. Therefore, these nodes E, F, C and G are called leaf nodes or external nodes. Now we can discuss about internal nodes. Internal nodes are defined as nodes that have at least one child. Unlike leaf nodes, they do not terminate the tree but instead act as connection point that lead to other nodes. They play a crucial role in maintaining the hierarchical structure of the tree. Let us analyze the given diagram. At the top, A is the root node. Since it has three children, B, C and D, it is also an internal node. Node B has two children, E and F, making it another internal node. Node D has one child, G, so it is also classified as an internal node. Node E, F, C and G do not have any children, therefore they are leaf nodes and not internal nodes. Now we can discuss about edge. An edge is the connection or link between two nodes. It represents the relationship between a parent node and its child node. Edges are essential because they form the structure of a tree and enable traversal from one node to another. In simple terms, if nodes are considered as points, then edges are the lines that connects them. Let us analyze the given diagram. Node A is connected to B, C and D. These connections from the edges A to B, A to C and A to D. Node B is connected to E and F, forming the edges B to E and B to F. Node D is connected to G, forming the edge D to G. List of the edge in the tree. The edge present in this diagram are A to B, A to C, A to D, B to E, B to F, D to G. Thus the tree contains a total of 6 edges. A fundamental property of tree is a tree with n nodes always has n-1 edges. So in this example, number of nodes equal to 7, that is A, B, C, D, E, F and G. Number of edges equal to 0. Since 7 minus 1 equal to 6, the property is verified. That is, a tree with n nodes always has n-1 edges. Now we can see about degree of a node. The degree of a node is defined as the number of immediate children that the node has. It indicates how many branches originated from that node. This concept helps us understand the structure and hierarchy of a tree. Let us examine the given diagram. Starting from the top, node A has 3 children, B, C and D. Therefore, the degree of A is 3. Node B has 2 children, E and F. So, the degree of B is 2. Node D has one child, G. Hence, the degree of D is 1. Nodes C, E, F and G do not have any children. Therefore, the degree is 0 and they are known as leaf nodes. Now we can discuss about height of a node. The height of a node is defined as the number of edges in the longest path from that node to a leaf node. It represents how far a node is from the deepest node beneath it. In simpler terms, it measures the depth of the subtree rooted at that node. Let us examine the given diagram. Leaf nodes E, F, C and G. These nodes do not have any children. Therefore, the longest path from each of them to a leaf is 0. So, height equal to 0. Node B. Node B has two children E and F. The longest path from B to a leaf is one edge. Height of B equal to 1. Node D. Node D has one child G. The longest path from D to G consists of one edge. Height of D equal to 1. Root node A. The longest path from A to a leaf is either A to B, B to E or A to D, D to G. Each path contains two edges. Therefore, height of A equal to 2. We can discuss about subtree. A subtree is a smaller tree that forms part of a larger tree. It consists of a node and all of its descendants. In simple terms, any node in a tree along with its children can be considered the root of a subtree. Let us examine the given diagram. Here, A is the root of the main tree and it has three children B, C and D. Each of these nodes forms a subtree. Identify the subtree. Subtree rooted at B includes nodes B, E and F. This is a nonlinear subtree with two children. Subtree rooted at C includes only the node C and it has no children. It is a single node subtree, also known as a trivial subtree. Subtree rooted at D includes nodes D and G. Every node in a tree can be considered the root of its own subtree. A leaf node forms a subtree by itself. Subtrees help break complex hierarchical structures into smaller, manageable parts. The original tree is also a subtree of itself. Now we can discuss about the binary tree. A binary tree is a hierarchical data structure in which each node has at least two children known as the left child and the right child. This structure makes data organization efficient and supports faster searching, sorting and processing operations. Now we can see some basic structure of a binary tree. A binary tree consists of the following components, that is root node, parent and child node, leaf nodes, internal nodes and subtree. We have already discussed about root node, parent and child node, leaf node, internal node and subtree. So now we can move on the types of binary trees. There are different types of binary trees. The first one is full binary tree. The full binary tree has every node has either 0 or 2 children. Complete binary tree. All levels are completely filled except possibly the last, which is filled from left to right. The next one is perfect binary tree. All internal nodes have 2 children and all leaves are at the same level. Next one is the balanced binary tree. The height difference between the left and right subtrees is minimal, ensuring efficient operation. The next one is binary search tree, a special type where the left child contains smaller values and the right child contains larger values than the parent. Some application of binary trees. Binary trees are widely used in real-world applications including searching and sorting, database indexing, expression trees, priority queues, artificial intelligence, file systems and hierarchical data representation. Now we can discuss about binary tree representation. The representation of a binary tree refers to the method used to store the tree structure in computer memory. There are two primary ways to represent a binary tree. The first one is sequential representation or array representation. The second one is linked representation or pointer representation. So now we can see about the sequential representation. In sequential representation, the elements of a binary tree are stored in an array. This method is particularly efficient for complete or perfect binary trees. There are some rules for storage. For a node stored at index I, left child is 2 into I plus 1. The right child is 2 into I plus 2. And the parent node is left of I minus 1 divided by 2 into left. So here the minus value indicates an empty position. Always the array index starts from 0 to 6. Now we can discuss about a program. So first one, the hash include IO stream. This is a preprocessor directive. It includes the input output stream library record for cout and endl. Using namespace std, this allows us to use standard library objects like cout without writing std scope resolution operator cout. Int main of, this is the main function where program execution begins. The next line is character of tree of 7 equal to A, B, C, D, E, null and F. Declares a character array named tree of size 7, and also it represents a binary tree using sequential representation. Each index corresponds to a node in the tree. Null indicates a null or absence node. The next one is cout, binary tree using array representation. Prints a heading on the console / and moves the cursor to the next line. For int I equal to 0, I less than 7, I plus plus, a for loop that iterates through all elements of the array, and also it starts from index 0 and ends at index 6. If tree of I is not equal to null, it will checks whether the current array element is not a null character, and it prevents printing empty or non-existent nodes. Ensure only valid node of the binary tree or display. The next line cout index I, then tree of I endl. It prints the index and its corresponding node value. Endl insert a new line and flushes the output buffer. Return 0 indicates successful execution of the program, terminates the main function. Now we can discuss about linked representation, also known as pointer representation. In this method, each node contains data and pointers to its left and right children. This is the most commonly used representation. In this approach, each node is represented as a structure containing 3 components: data, left pointer, right pointer. Data stores the value of the node. Left pointer points to the left child. Right pointer points to the right child. If a node does not have a left or right child, the corresponding pointer is set to null. Int main of, this is the main function where program execution begins. Now we are going to create the binary tree. A comment indicating that the following lines will create the binary tree using dynamic memory allocation. Node into root equal to new node of A. Create the root node with value A. New node A dynamically allocates memory for the node. Root is a pointer that stores the address of this node. Root to left equal to new node of B creates a node with value B. Assigns it as the left child of the root node A. Root to right equal to new node of C creates a node with value C. Assigns it as the right child of the root node A. Root to left equal to new node of D creates a node D, assigns it as the left child of node B. Root to left, left to right equal to new node of E creates a node E. Assign it as the right child of node B. Root to right, right to right equal to new node of F creates a node F. Assigns it as the right child of node C. The left child of C remains null. C out root node root data endl prints the value stored in the root node, and then the next line access the left child of the root using the operator. The next line access the right child of the root. Return 0 ends the program successfully. Now we can discuss about the tree traversal. Traversal is the process of visiting each node of a tree exactly one in a specific order. First we can discuss about in-order traversal. So here the function is left to root, root to right. So consider the binary tree given below. Look the algorithm. First we want to traverse the left subtree. Then we want to visit the root. Then we want to traverse the right subtree. So traversing from 4 to 2, 2 to 5. Then 2 to 1, 1 to 3, 3 to 6. So the output will be 4 to 5, 1, 3 and 6. Here is a simple algorithm. In this algorithm, first the root node will be checked whether it is present or not. If the root node does not exist, it will return. If there is a root node, it will check for in order and it will place the data to the left. Or if the data we want to be placed to the right, then it will be to the right. Now we can see the pre-order traversal. In pre-order traversal, first we will be visiting the root, then we will be traverse the left subtree, then traverse the right subtree. So here the output will be first we will be visiting the root node. So 1, then the left node 2, then we will be again considering the left node. So 1, 2, 4, then 5, then 3, then 6. Here is the algorithm. In this algorithm, it starts with the root node. Then it checks if root node is null. If yes, it will be returned. If not, it processes the root, print or use root to data, traverse the left subtree called pre-order, then traverse the right subtree called pre-order root to right. Now we can see the post-order traversal. In post-order traversal, traverse the left subtree, traverse the right subtree, then visit the root node. So the output will be 4, 5, 2, 6, 3, 1. Now we can see the algorithm for post order. First it will be checking the root node for null. If X is null, then we won't be proceed. If it is not null, then recursively traverse the left subtree, then recursively traverse the right subtree, then print the current nodes. We can move on to operations of binary tree. So there are 3 different operations: creation of binary tree, insertion of node in the tree, display of a binary tree. First we can discuss creation of binary tree. So let us consider the following binary tree. The root node will be 10 and the subtrees are 20, 40, 50 and the other subtree is 30 and 60. So normally in binary tree we will be constructing step-by-step procedure. So in step 1 we are going to create the root node. So from the diagram we know 10 is the root node. So first we are going to create the root node as 10. So we are storing in the node, storing the root points to the node. So in new node we will be inserting the 10. The next step we are going to add left child to the root. So from the diagram we know the next left node is 20. So we are going to insert the 20. So root to left equal to new node of 20. We have inserted the value 20. The step 3 we are going to add the right child to the root. So we know 30 is the next node. So we are going to place root to the right equal to new node of 30. Now we are going to place the leaves. So our leaves will be 40 and 50. So we are going to add the left node, new node of 40 to the left node of 20, and we are going to add the right node, new node of 50 to the right of the 20. So you can see the pictorial representation of the tree. In step 5, we are adding the node 30. So we are adding to the right node of 30. So root to the right, right to the right equal to new node of 60. So we have inserted all the tree values. In today's section, we have learned about the trees and the binary tree. I hope you have understand the concept. I'll be meeting you in the next video. Thank you.